So we're going to look at here how to use differentials to estimate the value of a particular expression that isn't a nice round number. Now, this procedure, this process is related to the idea of linear approximations. But the main difference with this kind of a problem is that you don't have to come up with a function, an equation where you can plug in a bunch of different values. So we will just come up with an estimate for this number. We won't come up with an equation that would allow us to estimate several values. Another aspect of this particular kind of problem that can be sometimes a little confusing for students, and I know I found it confusing when I was taking calculus, was that this kind of a problem, they don't really give you sort of all the information directly. In some versions of these linear approximation problems, they'll be really explicit about like, this is the function and this is the value you're going to estimate your linear approximation from, and then you're going to use it to estimate this particular value. And in this kind of a problem, it's all kind of assumed, it's buried in the problem, and we kind of have to tease it out. And so it's a little bit more challenging because students are like, well, what do I do with this? What you don't do is put it in your calculator right away, because that's not what we're asking for here. So the idea of using a differential is essentially we're going to approximate the change in y with a linear approximation. The linear approximation is based on the slope of the tangent line, so the derivative of the function, and then how far you are moving away from that point. So we're going to need to figure out, so what is our f function? What is our function that we're going to take the derivative of? We're also going to need to figure out the value that we're going to evaluate that derivative at. And then we're also going to have to figure out what delta x is. And then we can use those pieces to calculate our approximation for the change in y. And then from there, we can then use that to actually approximate the value of this expression. So the first thing to kind of keep in mind is the kind of thing that we're estimating. And so in this case, we're actually being asked to estimate the value of a cube root. And that means that our function is going to be the cube root of x. So maybe we want to evaluate several cube roots, but we're going to evaluate a cube root. If this was a square root, we would use the square root function. If this was a fourth root, we would use the fourth root as our function. But we're basically going to look at the structure of the number that we're calculating, and that's how we're going to tease out our function. Now, once we have the function itself, then we can go ahead and we can take the derivative. Let's see, so this is x to the 1/3 power, so that'll be 1/3 x to the negative 2/3 power, because 1/3 minus 3/3 is going to be negative 2/3. And then I can rewrite this as 1/3 cube root of x squared, like so. Now, I put it in this form because it's a little easier to evaluate sort of in the cube root form than it is in the negative 2/3 power form. Okay, so we have our function, we have our derivative, and the other thing we need to figure out is that we want to evaluate the derivative at a nice value. So nice, by nice, we just mean it's easy to evaluate in the original function. And so typically you want to pick an integer. If you're using a trig function, then you want to pick your nice value to typically be something like a nice, like a standard angle or something like that, something you can do in your head. But in this case, what we're going to pick is an integer, and we want to pick an integer which is a perfect cube. Ideally, that's what we want, because if we pick something that's not a perfect cube, then we haven't really solved our problem, because we're still dealing with a crazy number. But what we want is we want to pick a number as close as possible to a perfect cube that we can use to do this estimation. So 64 is a perfect cubed. It is 4 cubed. 4 times 4 is 16, times 4 again is 64. So that's our perfect cube. So we're going to let x equal 64, since that's going to give us the nicest answer for our derivative. And then from there, we can actually calculate our delta x. Now, delta x can be either positive or negative, so it's important to kind of keep that in mind. Once we pick our nice value, we can determine whether the value we're going to estimate is larger than the number we picked to be our nice value, in which case delta x will be positive. If the number that we're estimating at is smaller, then we would have a negative delta x. 63.8, for instance, that would be smaller and our delta x would be negative. But here we're estimating 64.2, and so our delta x is positive 0.2. Essentially, the difference between the value we're estimating and the value that we're doing the estimation at. So value you're estimating, value you're doing the estimate at, the approximation at, and that gives us a positive 0.2. Now we just start plugging stuff in. Delta y is going to be approximately. Now, if we plug in our f prime of 64, and I'm just going to write this out so that it's clear, f prime of 64 times our 0.2. Now, when we plug in 64, we need to plug it into this expression. So now we have to think about how we calculate this cube root of x squared. So don't square it first, cube root it first, and then square it. So the cube root of 64 will make the number smaller, and then you can square. Because if you try to square it first, and then you try to take the cube root of that, you're going to be working with really big numbers. It's not good. So the cube root of 64 is 4, and then we're going to square 4, and we're going to get 16. And so this is going to be 1 over 48 times 0.2, which is equivalent to 1 over 5. And so what we end up with is, I think, 240. Yep. 1 over 240. Now that's our change in y. And then to estimate y, essentially what we're going to say is this is going to be approximately the cube root of 64. So the value we're doing the approximation from, plus delta y, which we found to be the cube root of 64 is 4, and then plus 1 over 240. And then we can simplify that. 4 plus 1 divided by 240, 4.004166666. Or you want it as a fraction. Now, the only reason you should use your calculator is to verify that this approximation is about what you would expect it to be. And so if we actually take the cube root of 64.2, we can compare is 4.004162 ... And so what's nice about this is that 40416, all of these digits are the same as these. So 1, 2, 3, 4, 5 digits are the same. So don't be surprised if you're being asked to estimate differentials, if you're being asked to carry a lot of decimal places in your expression, because sometimes if you're not going very far away and the rate of change is not very, very fast, you may find that you have to carry out quite a number of decimal places for the linear approximation to deviate from the true value. Because the differences are quite small, and that's why the value of the linear approximation is so good. But if you do go far enough away, then of course, as we saw with derivatives, slopes of tangent lines themselves don't stay near the function forever. Eventually they deviate unless the function is itself a straight line, in which case you don't need to use any of this. But you would expect, though, that there would be, 3 or 4 decimal places typically, sometimes 5 or 6, where there really are very good approximations because you're staying pretty close to the true value of the function. But there will be a point at which the estimation and the true value differs. And the problem here is not looking for the true value, it's looking for the estimation. Now, back in the day when these techniques were invented, there were no such thing as calculators. You couldn't just go to a calculator to get the true value to do the comparison. But we do it here simply so that we can see that, yes, our approximation technique worked. We got a good estimate for the value. And so if we needed to do additional calculations, obviously without the aid of a calculator, then we would have a good enough estimate where we could proceed like this.